Log on, tune in, find out. Another good idea from Cambridge.
Looking at phase 2 and phase 3 together. And to be clear, the role of phase 2 here is dose finding. So you're trying to see, is there a dose response at all? And if there is, which dose should you choose? And then you're going to use that information to select your phase 3 design. And the reason for looking at them together is, well, if you're trying to assess how good a phase 2 design is, the real proof in that is, does it lead to a successful phase 3 trial? So you can't really separate these issues. And then you start thinking, well, if I'm going to ask that question, what do I do in phase 3? Shouldn't I make that design somehow based on what I've learned in phase 2? So you pretty soon get to the sort of problem that we have here. And it's an interesting one, I think, because it's really bringing things together. It attracts, it attracts me because I like looking at group sequential designs, and here we've got a sequential decision problem coming in 2 stages. So it's a bit like say a group sequential design within phase 3 in 2 stages. But it's also rather different, because if you're just looking within a phase 3 design, you've got one parameter. Here we've got models of a dose response curve. So at an intermediate stage, we've got, in a Bayesian setup, a posterior distribution on all possible parameters and therefore response curves. So there's going to be rather more to it. So in that sense, it's going to be different, but I think the fundamentals of how to try and tackle the problem, sequential decision theory, the way it's formulated and the way we approach it, should be somewhat familiar. The kind of questions I hope we can answer then, one of them came up yesterday. People talked about, it's a little bit strange. Phase 2, you tend to have a small sample size, and you're asking a very hard question. Is this dose better than this dose? Phase 3, where you're looking for a much bigger treatment effect because it's at the dose that's doing really well, you take a big sample size. So will that come out of this approach, or will we show that you should actually be doing something else? Well, let's try and find out. I've been doing this work in a pharma working group, and it's quite a big group. This set of names here refers to the people in the sort of core generic model. There are other subgroups working in specific therapeutic areas. So they're doing similar things, but with rather more detail about those particular conditions. And that's been really great, because the conversations we've had have been a lot of the time about formulating the problem. And we need to get the right ingredients. We've still got something pretty simplistic, and I'll go on to talk about the extensions one might have. But I think at the same time, it's simple, and it's got the core ingredients reasonably well. Well, you can tell me what you think about them as we go through the talk. So what I shall do is outline the elements of the phase 2, phase 2B maybe, if you want to call it that, for the dose finding rather than the proof of concept stage, and the phase 3 decision process. I'm going to set up a Bayesian problem, and I'll show how one can go about optimizing it. And then just taking the simplest version of everything, show some results. And then I'll talk about extensions, and finally look at one of them. And that's an interesting one where we make the phase 3 part a group sequential trial. So let's work our way through this. I'm assuming a particular parametric model for the dose response curve, the Emax model. So just to be clear about that, we've got a lower asymptote at theta 1, an upper asymptote at theta 1 plus theta 2. The ED50 at theta 3 is where you get half of that improvement. And then the fourth parameter denotes something to do with the shape and the steepness of that curve. We put a prior on the 4 parameters there. Fairly simple choice, which is meant to give a range of possibilities. Looking at theta 2 here, the improvement the treatment offers is typically positive, but it may not be very big, it may be negative, so we've got a treatment which isn't effective. Theta 3 and theta 4 have to be positive. They're pretty variable in this prior. So we're covering a lot of scenarios, some of which are good ones. The model for what happens in phase 2, given the dose response mu at dj, we're going to observe normal responses centered on that mu, variance sigma squared. And I've taken a simple setup here where we put 30% of the subjects onto the control, dose 0, and the other 70% are spread evenly over the doses. I'm going to end up with 7 doses in this case. So that's something that you might go back and say, well, why don't you change it? Why don't you try something else? But what I'm going to just do for now is say, let's suppose we assume we'll do that. What should N2 be? How big should the total sample size in phase 2 be? Once we observe those data, we can combine them with our prior distribution. We get a posterior distribution at the end of phase 2 for the model parameters. In phase 3, we get the same sort of responses on our phase 3 subjects, but of course now we're just comparing one selected dose against control. Now it's typical to be required to have 2 positive phase 2 trials. And each of those would normally be run with a one-sided type 1 error of 2.5%. To make life a little easier, I said let's combine those and have one big trial with a much lower type 1 error, which is roughly the square of 0.025. One reason for doing that is that when I go on to the group sequential phase 3, it's easier to tackle that when you've just got one trial. But that is something you might want to vary. We've got to complete the problem. We need model prior utility. So what's the gain function? What are the sampling costs? I'm taking as a unit the cost of one subject either in phase 2 or phase 3. So that could be anything from $10,000 to $50,000 in, say, some cancer studies. So one unit is actually in itself a lot of money. And if you get a successful product with a good patent life left, then you're going to make a lot of profit from it. And so the gain function, I'm assuming a value there which is taken from sort of various suggestions in the literature, 12,000. So that's 12,000 units, each of which is tens of thousands of dollars. So we're talking about many hundreds of $1 million as the outcome. So that's a realistic gain. It's a big win if you prove your treatment is effective. One thing that's very important is to do something to model safety. If that's missing, you're always going to take the top dose because we've got a monotone increasing efficacy curve. And the way that's included is by having a risk of failure due to safety problems, which is itself increasing in dose. And in this very simple setup, I'm keeping this independent of everything else. We're not claiming to learn about it in phase 2. So it may be that the evidence comes up in phase 3 and you have to give up your trial there. It may be that the risk only comes later after marketing. Whatever the situation, you lose your gain. Maybe you lose more than that if you've actually been treating patients and having bad things happen to them. So that will counter the tendency otherwise of just choosing the high doses. So that's the set of ingredients. And here's what we've got to do. Our actions are we can choose the size of phase 2. At the end of phase 2, and this depends on the data that we've seen, we can decide, do we actually run on to phase 3 or do we give up? And if we do go ahead, which dose should we select? And then how many subjects should we put in phase 3? So the things we're trying to optimize are, whoops, which way am I going? Backwards. Yeah. The things we're trying to optimize are choice of N2, the decision rule for proceeding to phase 3, and the elements of phase 3. You'll have noticed a lot of assumptions have gone in here. And you might think, well, if you were talking to people in a company saying, can we tackle our problem this way, they'd struggle to provide a lot of this information. I don't think this makes it an unreasonable approach because companies still make decisions. And if you think about it, those decisions do rely on these sort of things. So people may be making decisions thinking they don't really know costs and priors and so on, but they're acting as if they do. So it's interesting to try and see, well, what would happen if you did know? And maybe we should start trying to elicit that and see where it takes us. Okay, so let's tackle this optimization problem. And there's a schematic of what's going on. We can think our way forwards through the problem. So we've got to choose N2, but let's take a particular N2. So we fix the phase 2 sample size And the way I've set things up, that fixes the whole design in phase 2. So for one of those values of n2, we can generate data. We can simulate what's going to happen. So that means we generate parameters from the prior. We get a dose-response curve. We then generate subjects' responses on the different doses under that curve. And that gives us a set of data. So here you are at the end of phase 2, thinking, do I carry on? Which dose do I select? How big should phase 3 be? And what you've really got to go on is your posterior distribution for the model parameters and the dose-response curves. So the way to assess the options, you can take a particular dose, a particular phase 3 sample size, and say, conditionally, given what I know, what's the expected gain if I follow that route? And you find out by averaging over a sample from the posterior distribution. I mean, you'd like to integrate it, but you can't, so you sample. And then you compare all the different options of doses and sample sizes, as well as not doing phase 3 at all. And you find the right one for that phase 2 outcome. And then you work your way backwards. So averaging over all the different things that might have happened in phase 2, you get the expected net gain for this phase 2 sample size. And now we can compare different N2s and see which one wins. So actually, I think that's a fairly straightforward exercise. There's a lot of detail behind this on how to do it. I mean, there's one slide here it's just explaining that you can approximate an integral by a sum using sampling in the process. It does highlight the important point of why it's really nice to be doing this in a Bayesian. I think it'd be impossible not to do this in a Bayesian way. Because at the end of phase 2, all that matters is the conditional distribution. So you can optimize from that point onwards without worrying about what you'd have done in other circumstances. So I won't say much more about the details. I'll talk a little bit more about the computational burden and so on later on. But let's look at an example and see some results. So some details of the example. I've got 7 doses, the prior that we saw before. One thing to say a bit more about the ED50, the dose where you get half of the possible benefit. It's pretty spread out. So the mean is halfway up the scale of doses, and the standard deviation is twice that. So it could be way off beyond your highest dose. It could also be very close to 0. So we've got a lot of possibilities. And you can think, well, they're going to give quite different implications for which dose you'd choose and what you want to do in phase 3. The risk of safety problems, just got numbers here. The highest dose, there's a probability of 0.2 that everything then goes pear-shaped and you lose. Even if you had a successful phase 3 on efficacy, you lose all of that because it turns out you're unsafe in terms of adverse events. But lower doses, this is a quadratic shape, so lower doses, the risk is pretty low. Okay, so here is the bottom line for comparing some possible values of N2 in this particular setup. And in each case, the phase 3 sample size was allowed to range from 100 to 1,000, so quite a big, and that's per arm, quite a big range. And the expected net gain, so this is 12,000 times the probability of a successful outcome in phase 3. Right? That's your profit, minus all the costs for the N2 phase 2 subjects, and however many phase 3 subjects you decided to use, averaged over those options. And the maximum here comes at a sample size of 300 in phase 2. This function is fairly flat around there, so you might go up or down a bit. But remember that one of these units is $10,000 or $50,000. So even 10 on this scale is still maybe $500,000. So these are important size effects. Obviously, you can look much more closely into what's going on and try and understand what's behind all of this. And I'll just do a little bit of that. Let me say one thing first about the computation. This was a fairly low-key simulation. I was only using 500 replicates for my phase 2 data. I was doing 500 samples from the posterior distribution to optimize phase 3. This took a couple of hours or so running in R using loops, which must mean it's very inefficient and one could scale it all up. But I haven't, and I've kept this rather crude. Interestingly, if you look at the standard error on this number, 4795, it's about 200. So you might say, well, this is useless. However, one smart thing was done in the simulations, which was to couple all the scenarios. So comparing different N2s, I actually had the same generations of theta values from the prior, and coupling as far as possible the responses by using the same error term on the doses there. So if you look at the standard error for the difference between two of these numbers, it's 10. You'd expect it to be 200 times root 2 if you had independent sampling. So there's been a very big gain here, and that was pretty crucial to making this whole thing work. And you could obviously do larger numbers of simulations to get that 10 a bit smaller. But this is starting to take quite a lot of time, so we still have to think carefully when extending the problem how to keep the computation reasonable. Still looking inside the computations, what was going on. These histograms show the distribution of the dose that was selected, and then the phase 3 sample size. So there's a column here at 0, which means that we didn't do phase 3, didn't select any dose. And then in different situations, we've actually taken anything from the lowest to the highest. And the sample size has ranged all the way across lowest to highest. So we've been adapting very strongly to what we've learned in phase 2 in an optimal way, given this formulation. And clearly the safety risk variable is doing its job because we are keeping away from the high doses a lot of the time. Looking a little more closely, we can ask, how do things tie up? When we choose a particular dose, what had we seen about it? So this is showing the posterior mean of the expected response, or it's I think the difference between that dose and placebo or control. We're only using the low doses when they're actually showing themselves to be doing very well. What we're actually doing is comparing with the next dose up and saying, does the extra chance of a increased efficacy and higher probability of success outweigh the risk of losing due to safety problems?
I'm sorry, Chris. Gosh, I'm sorry. What is on the vertical axis of the plot?
Oh, the posterior mean of EY.
Thank you very much. Okay.
So and there's another graph where it's very similar, but we've got the probability of success in phase 3 on the vertical axis. So we can say similar things. We're choosing a low dose when it's actually got a very high probability of succeeding in phase 3, and so there was no need to increase to the next dose. That probability would have gone up a bit, but we'd have risked safety problems. And there's a big mass of stuff over here where I think what's happening is we've got dose response curves which are fairly flat, or their ED50 must be way off to the right. So even at the highest dose, we don't necessarily have a great chance of phase 3 success, but we still go ahead with a big phase 3 sample size. And because there's such a big gain if you succeed, it's worth running these when the conditional probability of success is getting down 0.2, 0.1, even smaller. It's a lot higher than type 1 error, though, remember, which is 0.0005. So we're not just tossing a coin. But I guess, well, down here it's certainly taking a pretty serious pump. Okay, so we can look inside, and we could look a lot further to try and understand what's going on. But let me talk about moving on. What else could we do in this formulation to extend this sort of method? And the list is very long, right? We can, within phase 3, we can go back to doing it properly with 2 phase 3 trials. But I'd like to see what happens with a group sequential phase 3 trial, see if that changes things much. We can take 2 doses into phase 3. Clearly, we've got a posterior distribution, we've got efficacy versus safety. There must be situations where you think I'd like a high dose because that will be effective and a low dose because that will be safe. Can we try them both? Is that ever worthwhile? The gain function, commercially, one should really think about net present value. So there ought to be a term in there that says how much time have you taken, how much of your patent life have you used up in this process with a long phase 2 and a long phase 3 study When it's positive, that will count against you. So that's a little bit different from just the patient costs, which you get all the time. What if you're taking 2 doses to phase 3 and they're both successful? What's the gain? I think it depends on the therapeutic area, but there will be places where that's rather better than just having 1 dose. In a company, there's something wrong with this formulation that will say algorithmically, okay, we go and do phase 3. What if we've got too many phase 3 studies in the pipeline? So what you should really be looking at is the portfolio management. How do you choose of all the options of what to do next, which ones will have their phase 3 study? And then you can go backwards and say, well, if we're going to do things that way, what do we need to learn in phase 2 to have the right information to make those decisions? Additional model features, we could be learning about safety in phase 2. Quite often you have a short-term endpoint in phase 2, so that's not the real endpoint that you're going to look at in phase 3. So what if you're learning about that? You'd have some correlation between those endpoints in your model, but they may not be identical. And going back to phase 2b, what about all the adaptive options in phase 2? Here's a nice framework for testing them. We've actually got a real measure of how well they're doing if they're actually helping phase 3. Computation, I've mentioned the coupling. That was a very key part of making what I did feasible. I didn't say much about the sampling. That can be done, sampling from the posterior, that can be done by MCMC, of course, but in this particular case, one can use some nice features about that 4-parameter model to reduce the complexity and actually get direct samples there. There may be some possibility of reusing Monte Carlo samples from one situation to another. If they're close enough and they're properly coupled, then rather than repeat all the sampling, you could use the same samples and reweight them by importance sampling to get what you need. And as we complicate phase 3, we're going to run into trouble. If at the moment, when I say what happens in phase 3, I just look up a normal probability. If phase 3 is group sequential, I've got to do a nested integral, Armitage McPherson row sort of thing to evaluate phase 3. I don't want to do that 500 times 500 times so many times. What I can do, though, is pre-compute a lot of cases, get a grid of results, and use that to look up and interpolate new situations. And there we're getting a bit closer to the philosophy of dynamic programming, where you say, I'm going to try and solve the late-stage problem and work backwards. We can't solve it quite in the same way as dynamic programming, but we can reuse a lot of work and save effort. So let's now look at one extension, making phase 3 group sequential. And all I did was say, everything else is the same, but within phase 3 we can have a 5-group group sequential test, fairly standard form, something I know is reasonably efficient. What happens to the results? Well, some interesting changes. No longer is 300 the right sample size, but 100 is the right phase 2 sample size. So there's been a big change. Phase 2, it's actually, we'll see, it's got a bit of a different role. And it's using fewer subjects. And whereas we had about 4,800, we've now got 5,300 as the expected net gain. So that's gone up by 500. And they're in units of maybe $50,000. So making phase 3 group sequential, 500 times 50,000, $20 million? $10 million? A large number, right? So that's the real benefit of group sequential methods. In the big picture, they make one heck of a difference. And what's going on? The chosen dose, the chosen sample size, these have changed dramatically. We've got more at the highest dose, and we've lost a lot of the situations where we didn't have a phase 3 at all. And we've got lots of high maximal sample sizes in phase 3. And I think what's happening is there are situations where we recognize the uncertainty about the treatment effect. And we say, well, the way to deal with that is by being group sequential. We have a big sample size, so if it's a fairly small effect, we'll have the power to detect it. And if the effect is bigger, we'll stop early. And if the effect isn't there at all, we'll stop early for futility. And so it's common sense, but I think it's being seen very clearly in this setup. And It relates to some of the discussion about adaptive sample size re-estimation.
But to clarify here, you plot the maximum sum size of group sequential or the
Oh yes, the maximum.
sum size?
So it's the N3 that was in the design.
Okay.
Yes. And it must be the case that we're not using that most of the time. These things are stopping early for one reason or another. So I think the possibilities are really very, very wide. I mean, endless maybe. You can just take this formulation and try and make it more and more realistic and put in the things that interest you. And I think we can learn a lot. And what I've really shown, I would say, is a proof of concept. One can formulate and tackle this problem. And I think the formulation is reasonable, but I'd be interested to hear what people think. But it can be developed further. The Bayesian approach is very important. It gives a very nice way of handling all the uncertainties all the way through. Computation, I'm sure, can become an issue if we complicate the problem. And, well, you know, there are things we haven't yet done. We haven't gone parallel. We haven't gone to cloud computing or whatever. So there are solutions to all of that. We can also look within these results and say, well, what's actually happening? Right? People have rules for doing things at the end of phase 2. Which dose do you choose? Is it the first one that's got a theta hat which is equal to 1.3 or something? Well, somewhere in the implicit stuff here, there is also a rule. So it'd be rather interesting to go back to the data and try and summarize what that rule is and see how it compares with what people might have expected to do. So I think there's plenty to do, and it's time for me to stop. Thank you.
Thank you very much. So we have time for some questions. Yes, please.
So this is all very nice, but could you comment on the pros and cons in this way compared to the so-called seamless phase 2-3 design?
So that's another variation on the setup where you might say, I think the key thing in my mind is, can you use the phase 2 data with the phase 3 data to make the final decision? And one thing, that's an interesting question, because I think one thing that we're seeing here in these higher sample sizes, we've sort of, in going to a group sequential phase 3 design, we've shifted data from phase 2 to phase 3. The phase 2 study is smaller, and the phase 3 study is bigger. And I said I was changing the role of phase 2 because it's no longer, well, it's answering the question, should we continue? And it's answering the question, what's the right dose? But it's not answering the question, and what's the treatment effect? We're saying we can deal with that in phase 3, and we'll take much more uncertainty, but we'll have a group sequential phase 3. So a seamless design would allow us to do more in phase 2, particularly if we piled up observations on the dose we're going to select, although I'm not sure how you allow for that when you take the data forward. But it's another option. I mean, I'm pretty skeptical about that now because that's a problem I've looked at. And the value of the phase 2 data, when you take it forward to phase 3 and allow for all the multiplicity and so on, it goes down. It's sort of, it's not worth the same number of observations in phase 3. It's worth about half of them.
Well, but yeah.
So that might sometimes be, and you get the logistical problems of making the whole thing seamless. But maybe I'm being more definite than I should in my conclusions. The other thing I can say is, here's a framework to try it out.
So Jane?
Yeah, hi Chris. This is a very nice presentation. A lot of interesting concept twist. I wonder whether you have considered the setting where you actually use a biomarker in that process, in the phase 2 part, or you have to deal with the real endpoints at the end.
So phase 2 would be like a short-term endpoint.
Correct.
Yes. In fact, a research student of mine, Frederick Kern, has looked at that problem as part of his PhD thesis. So he focused on that with a single dose. So, you know, you make one part more complicated, you simplify something else. And so our model there was that you have a phase 2 endpoint with effect theta 2, a phase 3 endpoint, the primary endpoint that you're really interested in would affect theta 3, and the prior model will have a joint distribution for those with a correlation between them. So that can be done, and I won't try and summarize all of Frederick's results in a sense, but there's quite a bit in common because he looked at things like should phase 3 be group sequential or not, and saw very similar patterns there that it became helpful to put more data in phase 3. Even more so there because in phase 2 you're not even seeing the primary endpoint, so you can't use that in the final decision. Now combining that with dose selection, which is what we really want to do, I'm not sure that, well, that was sort of on my list, wasn't it? But you immediately get interesting questions. How do you set up your model for dose response jointly for what you're going to have in phase 2, one endpoint, and phase 3, the other? They should be going hand in hand somehow, but need to build in the correlations. But yeah, that would be good to do. I mean, that would be, I think, an important thing to do to be realistic for a lot of cases. I mean, that's one reason why I think it's reasonable in saying you don't get much safety data in phase 2 because it's short and sweet and you don't get the length of follow-up. If phase 2 really had the full-term endpoint, you might want to model that.
Okay, thank you very much. In interest of time, we have a coffee break and we don't want to get over. So please come back at